right, welcome back. Really, you've had a nice weekend. Restful, staying on top of things. Okay. So we will continue today with our trek through mostly algebra concepts, although there is one calculus theorem that's in here today. Sort of lets us do calculus without doing too much calculus. So we'll look at that theorem, and there's a couple places in the homework where you'll need to apply that specific theorem. So we'll highlight it, do an example, and see how that works. So where are we today? This is Monday, October 3rd already. So we're going to take a look at 3.2. 3, 3, 3, 5 are coming up. Notice we don't do 3.4 or 3.6. And so we've got 3 more sections after this, which will involve looking. So today we're looking primarily at logarithms. But to get there, we're going to discuss some things about inverse functions in general, a little bit about exponentials, tie those together, but we'll start doing more and more calculus with exponentials and logarithms in 3.3, 3.5, and 3.7. So, this is, well, what are the mathematical operations that we use on a general basis? Multiplication and division. Before we learned multiplication and division, what else did we learn? Addition and subtraction. And what I'm going to show you today is basically we only have 2 operations that we work with: addition and multiplication. So far, that's all we got. Then we're going to tie in exponentials, which is sort of like a repeated multiplication, but so far, most of our math is just 2 operations. And the reason I say it's only 2 is because we learned facts such as 2 plus 3 equals 5. The reason I don't include subtraction as a different operation is because, as the way I'm going to present it today, it's really just the opposite of addition. So it's not new, it's just doing addition in the opposite order. Right? So we know we learned 2 plus 3 equals 5. Maybe we have flashcards to memorize it or something. We saw the 2 fingers and the 3 fingers, and that gives us 5 fingers. However, we got that fact down. When we go to learn subtraction, one of the things we sort of do is we take this fact that since we know 2 plus 3 equals 5, is we say, well, if I started with 5, and I did some sort of backwards operation to either 2 or 3, then I should get 2. And so we have to have a symbol for that backwards operation, and the backwards operation we come up with is a minus sign to subtraction. So 2 plus 3 equals 5, 5 minus 3 equals 2. So one of the things is you start to see facts are not just 2 numbers that we call them binary operations. We're combining 2. But those operation of 2 numbers always have an answer, so there's a pair. I guess you can't call it a pair. There's triplets. There's 2 numbers being combined into 1 number. So if we remember these facts as triplets, when we go to do the inverse operation, we're just reorganizing how the facts are laid out. And I'm going to start. The reason I start with addition and then we're going to go to multiplication is hopefully those seem like simple concepts. Yeah, we did this, and maybe you think back to when you learned subtraction that you actually did that. You didn't think necessarily subtraction. You went back and I remembered, well, 2 plus 3 is 5, so it must be 5 minus 3 has to be 2. So some of us did it that way. I know I did that when I start thinking about division, is I thought back to the multiplication table that you memorize, and you sort of think of it backwards. Okay. So when we get into algebra, we might do something like x plus 3 equals 5. And again, we were probably taught at one of our early algebra classes, you have an equation, and if you do something to both sides, you can do anything you want. So we looked at this to get x by itself. You subtract 3 from both sides, and you'll isolate the x. What I want you to think today is we can use the inverse operation instead of thinking of doing something to both sides, is just reorganize this as 5 minus 3, and we've solved for x. Okay. The reason I'm building up a little slow is that you're going to see how when I apply this to logarithms. Now some of you have no problem, you've used logarithms before and you're fine with them, but if you struggled a little bit, I think you might use this. This might be very helpful. Okay, so far, thinking of algebra just sort of as moving it to the other side, making it the inverse. So what does that look like with multiplication? Maybe 4 times 3 equals 12. And then again, what we do is we take our output, we take our answer, it sort of becomes an input, or is being combined with the number. And let's do it with the 4 this time. And again, we have to invent some kind of a symbol that means inverse. So we have the dot for multiplication, or maybe the x, and then a division sign, or maybe a fraction sign for division. And then we see this other piece. And again, we could do that with algebra too. We could say 4x equals 12. And so we could use this sort of inverse way of thinking of it. Well, if I take 12 with its inverse of 4, that's going to give me what x is. And since I know how to take 12 divided by 4, or at least I got a calculator that could do it, I can get that answer. And we're going to see with logarithms, as we treat them just this way, we will also be able to do it. Oftentimes we're going to go to a calculator to actually get those answers because, what's the log of 27 or we don't necessarily have those in our memories because we haven't memorized the exponential table. Well, wait, there is no exponential table, right? We don't memorize all that because there's just too many facts. So, but we're going to think of it getting the equations done this way. Okay, so inverse functions from algebra, we could do the same thing, right? We could think y equals x plus 2, and so when we start thinking of the inverse, the thing that's by itself is going to get a partner. The thing that had a partner is not going to be by itself. So kind of thinking of it as reorganizing with an inverse operation. So if we do this, we think of, with function notation, we have f of x equals y. So what would that look like with inverse notation? What would the inverse of this look like? So this, you put in x and you get y. Just in general, what would the inverse be? You put in y and you get x, right? So it's just getting us back. It's going the opposite direction. So again, we invent some kind of new notation, and this is not f to the minus 1 power. And that's one of the things you have to get over, because if it was to the minus 1 power, then that's 1 over f. That's one use of that symbol, but when we use it this way, we want to have it represent the inverse function. So when we put y into the inverse function, we get back to x. Now at the same time, we oftentimes do the inverse and the function itself on the same x and y axis, which many mathematicians would say is not right. Because if you take the inverse, y is the input, x is the output, you've actually got a different set of axes. Your units have changed. The x-axis now has different units, so it really should be done on the same axis, but yet a large portion of our education has done it that way, and so we're kind of stuck with it. So we see this thing where we switch the x and the y, and then we solve for it, and then even we use the inverse function as f inverse of x, so x is still the input into the inverse function, but we're actually getting backwards answers. So there's a little bit of confusion there, but we'll work through that. Okay. So we'll take a simple example of finding an inverse function. So I'll do f of x equals 3x minus 2. And again, if you see this, just from what we talked about, where there's multiplication, we should see some sort of division. Where there is subtraction, we should see some kind of addition now. So we should see those change because we know those are the inverse. The other thing that happens with an inverse is the order of operations will also change. Think about it. If you've ever taken something apart, when you go to put it back together, you put it in the reverse order because take it apart, it's now all in pieces. You have to put the inside pieces in there first because once you've got the outside, you can't get in there. So you've got to also go in the reverse order. So, and the steps that the textbook puts it in, they have 1, 2, 3 steps. I switch the second and the third steps mostly. So one thing they'll suggest to do is, well, f of x, let's just call it y because that's a little easier to work with, right? Then what we're going to do is we switch the x and the y. To me, that's the step of getting the inverse. The inverse takes the x and makes it a y, and the y makes it an x. That's what an inverse does. So I like to do that first. Again, our textbook says do it after you solve, but so it says solve for y and then switch. I say switch and then solve for y. So that's the step of making an inverse. That's sort of just reorganizing. And then now we solve for y, so we add 2 to both sides, or again, you could think, I'll do it kind of maybe more in standard. We'll add the 2, add the 2. If we go over here, we could think, well, the 2 is going to become a plus, right? You can do it this way. And then to get y by itself, we divide by 3. Or you could think over here, we do the inverse, so we're going to get x plus 2 over 3 equals y. And again, we could do that here. And we get the same thing. And we can see this, that now it's x plus 2 first, and then we divide by 3. So it's reverse operations in the reverse order. And then what we do at the very end, well, what was y? It was really f of x. So now what is it? It's really f inverse of x. And again, we're kind of back to doing this. And we have x plus 2 over 3. And just notice that that happens a lot, but there's a problem here. So if you're struggling with this because it doesn't seem quite right that the x on the left side for f of x equals 3x plus minus 2, it's not the same x as over here, right? If they're the same kind of operation, the x over there is actually a y. So it's, but again, probably 80% of our curriculum does that kind of thing. So we just kind of have to get used to it. And I think if we are aware of it, that it's kind of bogus, but they're doing it anyway, we get used to it. I have seen other systems where they'd write the inverse function, they would have the y there because that's really what it is. We're really plugging in the y value if those two things are connected. Questions? Okay, good. So there's a couple, I think there's 1 or 2 problems in here where they actually ask you to find the inverse, and it's just that process. And again, you should have done this in college algebra or a previous algebra class. So most of the stuff should be coming back, hopefully. Okay. So I think that's what, when I was making these notes, I had a bad sinus infection on Sunday, so I wasn't thinking real clearly. But here's this notation, and notice this notation is a little bit clearer. You know, x and y are actually, it's clear that x and y are really just switching places. And it makes it clear that the input of one becomes the output of the other, and the output of one becomes the input. So there's this swapping of places. And there's some things in the text, I didn't go through all of the stuff in there because, again, it should be a review of algebra. So they do have a few graphs in there, a few things, but I think I went over the homework, and we've got enough to get you started in there, moving forward and understanding. So the other thing is, since the inverse function undoes what the original function did, if we do a composition of an inverse with its function, we get back to where we started. And where do we start? We start with the input, which was x, so we end up with x. So we'll find that a function with its inverse works. And it doesn't matter which order we do it in, because each one is the opposite direction. You know, which way is forward? Anyone from Australia? We call it the land down under. Maybe we're down under from them, you know. So it's just where's up and where's down is relative. So it doesn't matter which way. Each time you take a composition of a function with its inverse, we get back to x. And again, they've got some other pictures in there showing sets and all this stuff from mapping from one to the other. And you're welcome to take a look at those in the text. But I wanted to get us where we can talk a little bit more specifically about exponential and logarithmic functions, because those are going to be the types of inverses that we're working with. The other thing we find, if we've got the domain of the inverse, it's going to be the range of the original function, and the range of the inverse is the domain of the original function. So it works both ways. And that makes sense, because if you switch the x and the y, you're switching the domain and range. So a lot of times they'll ask, you might get a question that asks you for a domain of something. It actually might be easier to find the range of its inverse or something else. Or they ask you for the range, and it might be easier to find the domain of the other function. And then you can swap it out. Okay, oh, that's right. So these are the steps that the textbook gives us. Again, basically what I did, but I do step 3 as step 2, and then I swap step 2 and step 3. So they say write it as y equals f of x, just so the notation's a little easier to work with. Solve the equation for x in terms of y. I do that after I swap them, and then they say to swap them, and either way it will work, but just the way I was taught. Right? Swap them first, because that's the inverse step, so you get there faster, and then solve for it. The cool thing with some calculators like Desmos, you could leave it, you could just swap the x and the y, and it will graph it as the inverse. You don't even have to solve for y after that. Okay. Some of the properties is that if you look at the graph of a function and its inverse, it'll be a reflection over the line y equals x. What's so special about the line y equals x? It's got points like 1, 1, 2, 2, 3, 3. If you take a point like 3, 3 and you switch the x and y, what do you have? 3, 3. So that's why it's sort of the mirror line, because you can't tell anything's been switched. So anything that crosses there will stay there. So that point stays, but every other point, the x and y switch. And so you get that as your reflection line, that 45-degree y equals x. So graphically, you'd be able to spot inverses. And then just this theorem, which is going to be helpful. And I didn't talk a lot about one-to-one functions, but the rule for a function is that each input has only one output. But it doesn't say that a single output could have multiple inputs. But then if we've got like a number 3 that has 3 inputs going to it, how do we know when we go back which one we're supposed to go to? You can't. So for a function to have an inverse, it has to be one-to-one. Each input can only have one output, and it has to have a unique output. It can't be shared, because otherwise we can't get back home. We might have 2 paths back. So that was sort of it. And so what it talks about, as long as we have a one-to-one function, we can find its inverse. And as long as that function is continuous, the inverse function will be continuous. So it just makes things easier for us. A lot of these theorems just say we can do what sort of intuitively we think we can do. Okay. Again, some of these, the textbook has proofs, and you're welcome to take a look at them. But those are things we need. Now, this is the one theorem. I looked at it and I thought, oh, it doesn't make any sense to me. Because what it's saying is that if you take the derivative of the inverse, right, that's this part here, it's the inverse function, and you're taking its derivative, at some point, that's somehow equal to 1 over the original function's derivative at the inverse function at the point. So, and there is a proof on this, and I sort of looked it over, but what it's what I did is I looked at the examples. What it allows us to do is to kind of get at least a value for the derivative of a inverse function at a point, if we're given that point, without actually getting the derivative. Because notice we don't have to take the derivative of the inverse, we take the derivative of the original function. And so sometimes that might come in handy. As long as we can get the derivative of the original function, we don't actually have to find the inverse function. And using this little rule, which let me clear off the screen because it make it a little clearer. This is something you're going to want to be able to use, and we'll use it on the next one. So just kind of remember what we're going to have. So the derivative of the inverse at a point is equal to 1 over the original function derivative evaluated at that point on the inverse. So let's pull up one from the homework. Actually, there's 2 in the homework, so you'll get a practice. You probably one similar to this, and then another one has another sort of thing. So we're given this function, and we're asked to find the inverse at 9. Okay, and okay, we could find the inverse function in general, but what does this mean if they're telling us the inverse function at 9? What is this value 9 really? Is it an x or is it a y? It's a y. It's a y. It's really a y. And so all we have to do with this, instead of going through and doing a lot of stuff, is just, well, it's really saying that 9 equals 9 x minus 8. So we're just going to solve for this particular value. Now, that doesn't help us if we had to do it for a lot of different points, but they're just asking for 1 point, so this might be easier. And so we could solve this, multiply both sides by x minus 8. I think it's the best way to do that. Distribute, you get 9x minus, is that 72? Equals 9. So you add 72 to both sides. 9x equals 72 plus 9 is 81. And then you divide both sides by 9, right? So we get that x equals 9. That's kind of cool. So the inverse at 9, y value of 9, has an x value of 9. If that's not confusing, I don't know what is, but those y's are 2 different values, right? So we now know the inverse at a point is 9. The second part they do is they ask us to use this theorem 7 from page 156, which is the one I had on the previous page. That's this theorem. I didn't list it, but if you looked in the book, that's where this is what they want you to do. Okay, so what we found out is the inverse at 9 is 9. So let's see if we can write that out, right? So that this is supposed to equal to the derivative at 9 should be equal to 1 over the function derivative of the inverse at 9. Well, we just found, because they asked us to, we just found the inverse at 9. Right? And what is the inverse at 9? 9. Yeah, it's right up there. So, okay. So what we have is we're going to get our answer. All we have to do is find the derivative of the original function. All we have to do, right? And that's what the derivative of the inverse function at 9 is going to be. Okay. So then what we do, and notice we haven't at any point really found the inverse function. So what we're going to do is here we're going to go, what is the derivative of this function? I'm going to rewrite this, and we could use the quotient rule. Actually, the quotient rule might be pretty quick, right? Because what's the derivative of 9? 0. And the derivative of the, so you could use the quotient rule, or I was thinking we could use this one as a and it's not really a product rule because 9 is a constant multiplier. We could just use the chain rule. The negative 1 comes down, so it's going to be negative 9 x minus 8 to the negative 2, right? Negative 1 minus negative 1, or negative 1 minus 1 gives us negative 2. And then the derivative of the inside, derivative of x, is just 1. I'm going to put that there to remind us we did use the chain rule on this. And so if I rewrite this, it's just going to be negative 9. This is the derivative, negative 9 x minus 8 to the negative 2. And so this is the derivative function. Let me write that down here. So all we have to do is find the derivative of the original function at 9. So that's going to be negative 9 over 9 minus 8. Not to the negative 2. It was negative 2, but when I move it to the denominator, it becomes a positive 2. How many of you make that mistake? I do it all the time, so unfortunately. But that's why I'm also a little kinder with partial credit. So we square it. Unfortunately, that's 1. 1 squared is still 1. So our answer is actually just negative 9. So this little thing down here is negative 9. So it becomes 1 over negative 9. So that's our answer. So we've got this little theorem that's been proved. Again, I can't follow all this the notation of steps, but I can use it to get the derivative of an inverse without actually ever having to get the inverse function itself. Okay, and this is helpful in case we've got one special point we want. We don't want to spend a lot of time, and some things might be more difficult to get its derivative. The other thing is when I teach like the brief calc for business purposes, remember, what is the derivative? It's the rate of change. It's the slope. Oftentimes in business operations, all you have is data. And then you could maybe from that data get a rate of change, but you don't actually get a function. And so something like this might be helpful because you're able to, just use rates of change. Does that make sense? Okay, so there's one this one came directly from the homework. I imagine you'll probably get slightly different numbers. There's a different one with a different function that they start with, but they do the same thing. And then there's a second part to this that asks about domain and range, and I'll let you take care of that from there. But this was the main thing. Like I said, I was almost going to skip this theorem. But then I looked at the homework and said, well, it's in the homework. Better do it. Okay. So now let's talk about logarithms. We're not done yet. No, that was all inverse stuff. Now we're going to take that inverse stuff and introduce what I call the log dance. So we have exponential functions, right? Something like 3 to the x equals 50. Okay. So that's an exponential function. What would the inverse function look like? Well, thinking back to what we did with addition and multiplication, we could kind of try to construct this. What we do know is that this 50 is kind of now, because it's an answer, it's an output, it's now somehow going to become some kind of input. The 3 and the x are going to be on opposite sides of the equation now because they were partners at the beginning. And so there's going to be some kind of inverse operation, and those are going to split sides. So we know there'll be some kind of equal sign here, either the 3 or the x. Since the x is what we call the input, right? Wouldn't it make sense that it now becomes the output? Hopefully it makes sense because it does. Okay. And then we need a new symbol for the inverse. And unfortunately, we don't get a vote on it, or they didn't ask us, but somebody came up with this sort of symbol that you do something like a log, and the base of that exponential becomes what they call the base of the logarithm. Okay? So that's all it is we make an inverse by switching inputs and outputs and then what was combined with the input is now over on the other side. And I call it to me, it's more of a dance than what we think of as mathematics, of taking an equation and doing something to both sides. But it's just a reorganization of three pieces, just like we did with addition to subtraction, multiplication to division. And so it gets you thinking of mathematics in a slightly different way, thinking of it as terms of patterns and maybe dance steps, you know. Not that I'm great with dancing. Usually I get kicked off the dance floor because I'm supposed to go left, I go right and step on people's toes, and it's not a pretty sight. But the log dance seemed to make sense for me, that it's just move the stuff around. The cool part is, I'm going to show you that if you take that same mentality, as just move these three pieces, identify the three pieces, move them to the right places, you almost, in an instant, solve the equation. So I got this piece that was left here, so I'm going to do that. But I realized when I gave this example, I haven't introduced what ln means. That's actually on the next slide, but we'll get there. So anyway, log base 3, so we've talked about the natural number, right? When we start talking exponentials, e, right? Okay, so e is an exponential. The logarithm that goes with that would be log base e of some input, right? And we use it so often that they said, let's not just put log base e for the books. It's just going to be easier to get a new symbol. Let's call it ln, which is the natural logarithm, and the base is sort of included there. Now, I don't know about you, but again, I mix things up left and right sometimes, but I noticed right away they call it the natural logarithm, but it's ln. And I know natural logarithm, n comes before l. Shouldn't it be nl? Does anyone know why it's ln? Does anyone? It's nothing to do with mathematics, or maybe a little bit, but because it's French. Napoleon Bonaparte, an emperor, tried to take over the world, I guess, was also a math teacher, or at least he wanted to standardize he was the one who invented the math textbook. So now you think he's really an evil person, but he invented the math textbook in France because that was going to set up his empire, that was going to rule the world, was going to do it through mathematics and logic and all that sort. So he set up these textbooks. And so logarithm naturel is how they would say it in French, of course with a nice French accent, and I don't have a good French accent, so I won't do that. And so it becomes ln, logarithm naturel, something like that. Okay, so that's your history lesson for today. So now maybe it makes more sense that it's ln, and you're not like me thinking for years, why do they call it ln when it's nl? But okay, so, and again, it has an input. So that's what we've got here. So one of the first things we do is we want to solve an equation. We've got to before we can do a log dance, we have to isolate either the exponential or the logarithm. Is the logarithm by itself? No. So let's get it by itself. Now we could subtract 17 from both sides, but I see that I've got a negative. So how about if I just add the logarithm to both sides? And it'll set it up nicely. Or just kind of move it over there if you want. You don't always have to do this as we've been doing. But I just want to show that's, this is the math I'm doing. So a minus and a plus, those become 0. So we get 17 equals the natural log of 4 minus x. And now after going through all of that, saying the natural log, what I'm going to do is I'm going to rewrite the natural log as log base e, because I need to see that base. Because when I do the log dance, I'm taking that base and making it an exponential, and I'm taking the answer and making it an exponent. Okay, so I want to make this sort of clearer by doing that. You might not need to do that. You might see ln and say, oh, I know it's got a base e, so I'll just do it. But for me, I like to write everything out. So when I do the log dance, here's the log dance. Notice there's two things on this side, And so we're going to make it into an exponential. So let's put the 17 that's by itself right now is going to get mixed with one of these two. And with logarithm, the base becomes the base of an exponential. The answer is the exponent. And then what do we have left? 4 minus x. So what happened to the log? It got danced out. It's just part of the dance. Once we do the dance, we don't need it anymore. It sort of gets replaced by the exponent, because I guess we could have that little symbol, the little caret, but that's the log. We're now using the inverse symbol. And we basically solved it. We're not quite done, right? We would subtract 4 and then divide by -1 to finish solving for x. But we've got the major part of this done. And this is the part most people would get stuck at. How do I get a logarithm and turn it into an exponential? And most of you were probably taught, if you were taught like I was, to take the exponential of both sides, and it just seemed like something weird. But this will work. And again, we would subtract 4 from both sides, and then we'll divide by -1. So when we do this one, and notice this is coming from the homework, so you'll see, you'll get a chance to do this. You get that x equals negative e to the 17 minus 4. Now you could distribute the negative sign through if you want to, but notice I subtracted 4 from both sides, and then I divided by -1, or multiplied by -1, and that's how I got that answer. So, a little. Okay. How are we doing on time? Oh, we're still okay. Okay. So let's do the same thing with exponential. The cool part of this one, and again, it also comes from the homework, so this exponent is all one thing. So 1 minus 4x is all up there. Log dance, right? It will solve it. So when we're doing the log dance, the thing that's by itself, which is the output of this function, is going to become the input of the other function. The other function, the inverse function of any exponential, is always a logarithm. The base of the exponential becomes the base of the logarithm, and then the exponent becomes the answer. Okay. And it's like it's almost solved now. The rest is just algebra, but we've made that transition from being an exponential function now to being a log function. We can clean this up a little bit. Log base e, let's go ahead and write that as natural log of 8. Now we could plug this in a calculator, but oftentimes logarithms have many decimals and are rounded, so a lot of times they like us to leave it in exact form. So we'll do that. And again, the rest is just algebra, so we subtract 1 from both sides. Let me go up here. So we're going to get natural log of 8. And I like to put parentheses around it just to emphasize what's in the logarithm, what's outside the logarithm. Equals -4x. Divide both sides by -4. And again, there's our answer. If you want, you can move the negative to the top and switch the order, or you could just leave it. I'm of the mind to just leave it as it is. Okay? But it's just that log dance. Okay? Think of, yeah, 3 things, you're just juggling their order. And that moves you from an exponential to a logarithm, or a logarithm to an exponential. So far, so good. We've got the 2 special bases, one we've already introduced you to. So log base e of some number gets written as natural log of that number. The other one we have is that if we have log base 10, that gets used so much that They call that the common logarithm because it's powers of 10. Earthquake scale, the Richter scale, is based on a logarithmic base 10. So you go from a 6 to a 7, that's 10 times more powerful. One, a step of 1 is 10 times more power. And so they just write that as log of x. So it's not that they forgot to put the base, it's just that it's a base 10. Okay? So sometimes when you're working these types of problems, you forget, if you go to make it an exponential, you forget it's got a base 10. But you got a common log is base 10. Every other base, they have to write what the base is. Okay. So what I like to do now is introduce the 3 laws of logarithms, but tie them into how they look with exponentials, because we've been working with exponentials, right? And since we do mostly natural logs, or using the natural number, if we have e to the a times e to the b, what's that equal to? E to a plus b. We add the exponents. What that looks like for logarithms is it would be if we had the natural log of a plus the natural log of b, again that's equal to a single natural log of a times b. Okay. So notice it's kind of the same thing, but it's sort of different. The addition here is out, you've got actually 2 logarithms, and then when you get a single logarithm, that's where the multiplication. With exponentials, the addition happens with the single base, and then the multiplication happens with 2 bases. So but that's because they're inverses. And the reason these are probably still so much a part of our curriculum is this is how, has anyone heard of a slide rule? Engineers? Yeah, but something used in the 60s. My dad, used to have my dad's, I can't find it, I don't know how to use it, but that's what they had before calculators. They were based on logarithms, and these properties was how you did multiplication and all that kind of stuff. The other one over here, what if we had e to the a divided by e to the a? Sorry, not e to the b. Give it something different. We could have done that, but what's that going to be equal to? A minus b. So in logarithms, that looks very similar. Natural log of a minus natural log of b is going to become division within a single logarithm. And with these, when we got these equal signs, we could go either way. So sometimes we're given a single logarithm and asked to write multiple logarithms. Sometimes we're given multiple logarithms, asked to get it into a single one. It just depends upon what we're trying to do. Okay, so we'll use these properties as needed, mostly in solving equations and such. And there's one more. So if I had e to the a raised to the b power, what does that become? E to the a times b. And so with logarithms, that looks similar. We have the natural log of a raised to the b power. What that becomes is the exponent becomes multiplication down in front. So it allows us to get the exponent down. And so those are the 3 main properties we use of logarithms to solve ones. We'll go to one in the homework. We're going to be asked to expand one. And then they've got a couple, there's a limit problem, which looks kind of intimidating because they have 2 logarithms, and I'll just give you the hint, make them into 1 logarithm, and then it falls into place fairly easily after that. But make it into 1 logarithm. So here's one where we're asked to make it into, to expand it out. And what you have to see here is that there are 2 pieces in the top, 2 factors being multiplied. There's a denominator, so there's a division here. So what is multiplication going to become? Addition of 2 logarithms. What does division become? Subtraction. So what I find is instead of trying to do this sort of step by step, is I'm just going to rewrite this natural log of x to the 13 plus natural log square root x minus 1, and then minus from the denominator the natural log of 3x minus 13. Now, are we done? There's one more logarithm property we had, is that we can take those exponents, put them out front, and that's what they asked us to do. So this one's going to come up front. And remember, the square root is really a 1/2 power, so that's going to come up front. So our final answer will be 13 natural log of x plus 1/2 natural log of x minus 1 minus natural log of 3x minus 13. And again, what it does is it allows, if you're using calculations with the slide rule, you don't have to take exponents, you multiply. So you get a number and then you multiply it. And there were people who could do those very quickly. I don't even understand them. So, okay, almost there. Change of base formula. So we have on your calculators, you have two main logarithms. You have the natural log and log base 10. If you need to use any others, there is a lot of ones have a math key where you can get these log base, but let's say we want to get the log of base 13 of 57. We could do that with the natural log simply by taking the natural log of 57 divided by the natural log of 13. So that changes, we're able to use the base e, the natural log, instead of base 13 and get the same answer. Okay. Or if you've got a calculator that has a log base, I just use that one. But however you want to do it. I had one calculator only had the natural log out there because you can convert them all over. The other thing you'll see is on a logarithm, when you graph them, the graph goes something like this. So the range is from negative infinity to positive infinity, but the domain is from 0, not including 0, all the way to infinity. And again, you'll see in the text they'll do a limit, they'll just sort of define that the limit as x goes to 0 from the right, from the positive direction, of the natural log of x equals negative infinity. So there's a couple definitions in there, but that's what the, oops, let's go back. Oh, here it is. That's this one here, yeah. So that's in the text. Also, as x gets large, logarithm does get large very slowly. So know the one-to-one property that lets us know we can get an inverse, use the laws of logarithm. There's 10 questions in the homework. Start working through those and get a little bit back more into calculus on Wednesday. It's some of the basic, I haven't actually looked at it myself, but it's basic derivatives. So they kind of, these are the things you have to know for the next class. We'll have some kind of study for it. They have a study guide. Hi.
I just had a quick question. So if I happen to miss a test, will I be able to where
I'll work with, I did, someone had that, what I did, you can, the next class, and you can send during office hours. Inside that 2 hours. Yeah. Or if you know you're going to miss it and want to take it early, sometimes, they don't get it to me, they'll like.
Okay.
Best thing is just something happens, just contact me and we'll make arrangements.
Well, thank you so much. Have a nice day.
You too. Hello.
Does it bother you when people talk? Do you hear them?
I do. And I don't know. Yeah.
Like it happens like every time, and today I'm like not in the mood, so I was just like, I want to know if he actually hears them because I don't think they really listen. You have a lot of patience. You're a good professor.
Yeah, but then sometimes I let it go for a while. Like last time I said, you know, this is a parabola and all your voices come to me. I'm at the center and it's hard for me to concentrate. But then it gets, you know, and sometimes they're talking about math. I see them explaining, but sometimes they're not. And sometimes they're authentic. And so yeah, it's.
I was just curious. I just want to know if you're them or not.
And today I'm just kind of like,
Yeah.
I've got this sinus headache that it makes it worse, but then it's also like, I just don't want to deal with this. Let me get done with this class. And yes, it does. And when someone like you lets me know that it bothers you too, you'll see Wednesday, I'll bring my cop hat.
I'm ready. I'm ready. Every single time I just want to please let me know the situation. But it'll feel awkward and like,
I know. I'll take care of it. Thank you. Okay, bye-bye.